Okay, hello everyone. This is Payman. I hope you have all enjoyed your long weekend. Because of the long weekend, we didn't have the tutorial session today, and instead of that, I'm preparing this video for those of you who were attending the Monday session and cannot attend the Tuesday session. However, if you can attend the Tuesday session, you're very welcome to do that. In this tutorial, we're going to cover active filters. So if I bring my laser pointer here, the first problem we're going to work on is design of an active low-pass filter with a DC gain of 0.25 and a corner frequency of 500 Hertz. So it's giving us the information that the feedback resistance RF equals to 20 kilo ohms. So for active filters, you know that we use op amps and they help us to gain higher inversion gains, and also we can kind of isolate two part of our circuit so that we don't have loading effect on a part of our circuit. So this is the structure of a low-pass filter, an active low-pass filter. We have Ri, the negative terminal of the op amp, negative input of the op amp, and we have RF and CF that connect the negative terminal to the output. So the circuit we can draw for this amplifier is like we modeled the impedance connected to the input terminal with Zi, and the impedance connected between input and output as ZF or Z feedback. So the ratio for this amplifier, the transfer function is VO over VI, so output over input, and then it's equal to minus ZF over ZI. So if you write a KCL here, you can get this relationship, because you know that the op amp rules, we have no current going into the terminals, and that the potential of the positive and negative input are the same. So using those rules and KCL in this node here, we can write this transfer function. So if you put ZF as the parallel connection of RF and CF, so we write the impedance, equal impedance for CF here, and these two impedances are in parallel. As you can see, RF and CF are in parallel, so the resulting impedance will be RF over j omega times CF over RF plus 1 over j omega CF. And if you simplify it, it will result this RF over 1 plus j omega CF RF. So this is for the ZF. We also have a ZI, so if we form our transfer function, our ZI is now Ri, and then we can write the transfer function as RF over Ri with negative sign, which is the DC gain, and then we have this frequency dependent gain, which is 1 over 1 plus j omega CF times RF. So here you see we had this before in passive filters. This is a low pass filter, and the corner frequency for that is 1 over RF times CF. So the question asks us to have a DC gain of 0.25. So the DC gain in this transfer function is RF over Ri, and if we put RF over Ri equal to 1 over 4, then we have Ri equal to 4 times RF. And also it gives us the corner frequency to be 500 Hertz, so in radians it will be 2 pi times 500 radian per second. And if we put omega c equal to this number, we can have a relationship between RF and CF. And if we select RF to be 20 kilo ohms, then Ri will be 80 kilo ohms with this relationship. So if you put RF 20K, this will give you 80K for Ri. And if you put RF in this formula here, we'll get the amount of C, which is approximately 16 nanofarad or 15.915 nanofarads. So this is the first problem. It's pretty easy. Just need to know this structure. And then this is something general we can use for the active filters. So you need to determine ZF and ZI, and then you can go ahead. So this filter is actually an inverting filter. So you get the inverse of the voltage at the input at your output. And then you have a frequency dependent gain as well. Okay, then we move to the second problem, and in these problems says design an active first order high pass filter with these gains. So h of s is minus 100 times s over s plus 10, where s equals to j omega. And it tells us to use a 1 microfarad capacitor. So the general circuit for a high pass filter, first order high pass filter, is a series connection of Ri and Ci at the negative input of the op amp and Rf as the feedback impedance. So again, we use this inverting relationship between output and input. So we have h of omega equal to Vo over Vi, which is equal to minus Zf over Zi. And so Zf is Rf, and Zi is the series connection of Ri and Ci. So this is the equal impedance for Ci at different frequencies. So a series connection of them will be Ri plus this impedance. Then if we simplify it, we have minus j omega times Ci times Rf over 1 plus j omega Ci Ri. And so we know that the corner frequency is 1 over Ri times Ci. And then if we get this relationship, and instead of j omega here and here we put s, so we have this relationship right now, and we need to compare it with the relationship that is given in the question. So Ri times f should be equal to 10, and Ci times Ri should be equal to 1 over 10. So we go ahead with this. So from the first relationship, if we use a 1 microfarad capacitor, we can find Rf, which is 10 mega. And then from Ci times Ri equals 1 over 10, we get Ri equal to 100 kilo ohms. And if we want to draw the circuit, it will be something like this. So we have 100 kilo ohm in series with 1 microfarad, and we have a 10 mega ohm as the feedback impedance. So if we want to examine this circuit in extreme frequencies, if we go to DC, we have an open circuit here. So if we have voltage here, no current will be there, and then we don't get any output. But if we go to very high frequencies, this will change to a short circuit, and then we get minus 10 mega ohm over 100 kilo ohm gain. And this, you can examine that this is a high pass filter. We go to problem 3. In problem 3, it tells us a general first order filter shown here. So it's not one of those that we learned about, but a custom made filter, and then you can extract a transfer function. So we want to prove that the transfer function equals to this expression. And for that, what we can do is writing KCL in this node and also this node. So if we name the voltage in the negative terminal, which is also equal to the voltage on positive terminal VI, then on this node we can write KCL, so which is the first expression here. Go VO minus VI over R2 plus VO minus VI times j omega C plus Vs minus Vi over R1 equals to 0. So it's KCL at the negative input terminal of op amp. And in the positive terminal, we also can write a KCL, which is Vs minus Vi over R3 equals to Vi over R4. So this KCL gives us a relationship between Vi and Vs. So at the end, the transfer function will be Vo over Vs. So we want to somehow get rid of Vi in our relationships. So if we simplify this expression 1 here, so we separate all the terms containing Vo here and all the terms containing Vi here and all the terms containing Vs here, then we can use this relationship and substitute the Vi for its equivalent amount, which we can get rid of Vi, and this time instead we only have Vo and Vs. So if we write Vo over Vs from this expression, will be this part over this part with a negative sign. So we write Vo over Vs equals to R4 over R3 plus R4 times 1 over R1 times C plus 1 over R2 times C plus j omega minus R3 plus R4 over R1 times R4 times C, and in the denominator we have j omega plus 1 over CR2. That will result in this expression that was given in the question. So I'll be covering these again on the Tuesday session. You are very welcome to attend if you have time. If you don't, you can review this video, and if you have any question, you can email me on my email. Thank you very much.